Hello, my name is Dmitry Soshnikov. I am cloud developer advocate at Microsoft, and I also work as an associate professor in a couple of universities in Moscow, Russia, teaching artificial intelligence. It's my pleasure to welcome you to the section on reinforcement learning. Reinforcement learning is one of the most exciting areas of machine learning because it allows us to teach machine something which we cannot do ourselves. As an example, reinforcement learning was responsible for computer winning in chess and in games such as Go. You know that computer now plays better than humans. And why? How can we teach computer to do something which we cannot do ourselves or cannot do as good? This is possible because a computer can play chess with itself a lot of times. And because he does it really fast, um, it's possible to do a lot of combinations and explore large portion of so-called search space. So the main idea of reinforcement learning is that computer will try to behave in some kind of formal environment and learn by doing that. It's in a way similar to a child. When a child is born to a new world, he tries to explore his surroundings, his environment, tries different ways of behavior, and soon he learns what he needs to do to achieve his goal. For example, getting food or getting the parents' attention. In the same way, for reinforcement learning, we need some kind of environment and an agent who will behave in this environment. For example, let's consider the simplest problem, pathfinding in a maze or in some sort of a labyrinth. So here we have a human being, and to train reinforcement learning algorithm, we need a goal. So at any part of the game, we can perform one of four actions. We can move up, down, left, and right until we reach our goal. And the goal in this case would be to reach the apple, to find the apple. And initially, we don't know where the apple is. So the problem is quite complicated. Um, to formalize the goal, we need to give a kind of reward function to every action. So, for example, if we moved to some place and we found the apple, we can give ourselves a reward of plus 10 points. If we encounter something dangerous, like we encountered a wolf and we were eaten by a wolf, or we encountered water and we have drowned, that is minus 10 points. And then if we just moved and nothing happened, we can give some small negative reward because we get tired by just moving around without any results. But the interesting thing is that when we start moving, we do not know immediately which way to go. And we do not know that until we reach the final goal, until we find an apple. And only then we get some substantial reward. And this is the main difference with the machine learning problems that we have encountered before. Because before, for every input combination, we knew the desired output combination. Now, for each state, we don't know where to go. And we can do that by trying, by exploring the surroundings. Initially, when we don't know anything about this map, we would move randomly. This is so-called random walk. And if we move randomly, at some point we will find an apple. On two-dimensional space, we will do that with probability equal to 1 at some point in the future. But that would definitely be not the shortest path. So how can we explore the surrounding and learn to find the best way? We can use the algorithm called Q-learning. And the idea of Q-learning is pretty simple in the beginning. It is driven by so-called Q function. Q function is a function of current state and action. So for every place or for every position on the board and for every action, we will get some number. And this number will show how good this action will be. In the beginning, the numbers will be all equal because we don't really know where to go. But once we start exploring the surroundings, we can use the principles of dynamic programming and so-called Bellman equation, which would say that if we are in a certain position, in a certain state S, and we perform the action A, the goodness of this action would be the rewards that we receive immediately, plus some reward that we might receive later. And we can estimate that reward by selecting the best next move and selecting the highest value of Q function at the new state across all actions. This may sound a little bit complicated at first, but please go dig deeper into our code and you will see that rather simple program can in fact fill this queue function by trials and errors and produce the good result. Uh, what's important as well is the balance between exploration and exploitation, because at some point, once we already know the queue function, the agent would likely to go according the known paths. But we need also to explore some places where we haven't been before. So we would perform experiments, sometimes going in a random direction, in order to fill in all places in queue function with some values of the best action. So after learning, we will end up having this map. So in fact, queue function shows us the map of the surroundings with likely directions where to go. And you can see that those directions in fact corresponds to the points we likely want to visit, like trees or apples. And at the end, you can see that the agent learns to do this quite well. He learns to find an apple from any position on the board. He does it reasonably fast. There are some other tasks, of course, that can be solved by reinforcement learning. We will also consider a task called balancing a pole, which is something which can be useful in programming things like segways or doing some industrial automation. In fact, reinforcement learning is not only for toy problems. You can say that chess is also a little bit a toy problem. But there are, in fact, many areas where reinforcement learning can be applied. So, for example, as I mentioned, industrial automation is an important area, and Microsoft has the project called Project Bonsai, which contains specific low-code tools which allows us to train reinforcement learning agents for industrial tasks. And in fact, this area of teaching an agent to behave is called machine teaching, unlike machine learning, because we design experiments in the simulator in such a way as for the agent to learn something, they learn best algorithm and best behavior. Reinforcement learning can also be applied for trading, because that is the dynamic environment which also reacts to our actions, to our behavior. It can be, of course, applied to robotics and self-driving cars, because self-driving cars are really very similar to the problem that we have been solving in this course with finding a way in the maze. Things like bid optimization, even some natural language processing tasks in question and answering, optimizing answers of the computer, can be tackled with reinforcement learning. So this is very exciting topic, and please, I hope you enjoy it and have the great study. Thank you.